Hey everyone, Jerry here. Welcome back to a very special edition of the LlamaIndex Webinar series. Today we're super excited to host Building RAG in Production, co-hosted with Anyscale, so that we teach you how to build RAG, not just kind of like the basic version, but actually do some of the stuff to make it production ready. So to make it scalable, add evals, actually try optimizing your retrieval techniques. So we're joined by Simon and Adam today. So Simon's co-founder, CTO, LlamaIndex. Adam is at Anyscale. And so we're really excited to put this workshop together with the Ray folks. And this is a lot of this material is taken from Ray Summit a few weeks ago to really share with you guys. And so we have a lot of really good stuff prepped. So let's take it away. Next slide. So yeah, Simon, feel free to jump in as well, but basically the main outline of this course today, it's going to be on build, evaluate, and optimize. I think there's 3 notebooks here. I think this will be roughly like interactive, but it's fine if you just want to follow along on the webinar. I think there's like an attached repo as well as notebooks that you can try to follow along with as well. And everything will be recorded, so don't worry if you actually miss stuff. We'll put this out on our YouTube for everyone to follow along.
Yeah, just to add a little bit more. So this is going to be a multi-part workshop. The total content will be approximately 3 hours in length. So this will be the first course on that, specifically about first understanding the capability of Ray in terms of scaling up large language model applications, and then going to a little bit more hands-on in specifically working with the Jupyter Notebook to understand how we can build a retrieval augmented generation system leveraging LlamaIndex and Ray. So as we mentioned today, the focus is going to be on a building component. And then for the next 2 courses in the series, we'll talk a little bit more about evaluation as well as optimizing the retrieval augmented generation system. So to start, let me say a few words about LlamaIndex. So as you guys have already known, LlamaIndex is a data framework for large language model applications. We provide an essential toolkit for you to build applications that contain ingestion, indexing, and querying capabilities, and that allow you to orchestrate over different components in a large language model application, including the large language model itself, different embedding models for you to be able to run retrieval, vector databases for you to store those embeddings and associated content, and also graph databases for you to be able to index data in a graph format. And it's been the essential toolkit for people to build application over retrieval augmented generation systems, conversational agents, as well as more nuanced data agents as well. So Adam is the expert on Ray here, but I'll say a couple of words about this before he goes into the details. So Ray is really the distributed computing system to help you scale the whole machine learning pipeline, as well as we'll be leveraging it to build a large language model application today. So there are various components at different layers of abstraction. So the Ray data helps with scalable embedding generation and indexing. You can use Ray train to do distributed training and fine tuning. And lastly, you can leverage Ray serve to serve scalable application deployments. Now, gonna hand it over to Adam to talk a little bit more about scaling large language model application with Ray.
Awesome. Thank you for that great setup and introduction. I'm gonna start my screen share here. All right, so yeah, so I'm excited to talk a little bit about scaling LLM apps with Ray. And to kind of set this up, I want to take a little bit of a step back and talk about scaling and distributed compute in general. Sometimes, depending on what your background is, like some folks coming out of ML research or coming out of different engineering disciplines may not be as familiar with some of the challenges with scaling. So we know there are tools that will help you scale training, like there's lots of great stuff out for that. There's some other things that will help you scale serving. And it may not be clear what the challenges are and why it's interesting to use kind of the right framework that, like Simon said, allows you to scale the entire ML stack and build kind of custom applications that completely work at scale. So you may be familiar with some of these thinking patterns already, but just to kind of recap, Why would you want to scale? Well, you want to do fine tuning faster. You want to do your pre-processing faster. So maybe generating, embeddings faster, or metadata, doing image processing. You may want more capacity for end users or other parts of your company or system that are clients to your LLM services. And even if you don't need all of that, you might just want better resource usage. So it turns out that one of the things that you kind of get in the process of building a good scalable infrastructure is a way to put individual pieces of processing exactly where they need to be. So things that need a GPU can be on a GPU and just use what they need. Other things that are maybe more concerned with data movement or CPU processing can end up on other resources that are less expensive. So those are all reasons why we would want to scale. So, right, so why is this hard? So again, just for folks, if you haven't played around with this kind of area before, sometimes it seems like, well, isn't scaling just having a bunch of machines and running the same code on lots of those machines? Like, how hard can that be? It turns out that that part's not so hard, but there's a lot of stuff that is hard. So the easy things where you're just basically running the same thing on lots of machines, that's called embarrassingly parallel processing. And that part is relatively easy. You may have even built a framework like that on your own at some point for a project or for school or something like that. But then there's a bunch of hard stuff. So managing dependencies. If we have a complex set of code, we have lots of routines that depend on others, and we want to schedule things in as parallel a manner as possible. But of course, we need to respect the dependencies. We can't run something before we have available the data that it depends on. So once you have a big complex dependency graph, managing those and putting them in the right place gets really tricky. Optimal scheduling. So just scheduling stuff, if you don't care how efficient it is, that's not too hard. But if you want optimal scheduling, that's a really, really hard problem. So it's kind of like an n-dimensional kind of bin packing over time kind of problem. And that's kind of what we get involved with when we're talking about complex sets of code that we want to scale. Minimizing data movement. So at scale, it turns out that just moving data around gets really expensive. You've probably experienced this if you go to pull down a terabyte of data from S3 or even just moving model weights around. So we have to be really thoughtful about not moving data when we don't need to move it. So that may mean moving code. It may mean kind of changing where stuff is read from and written to. Multi-tier data storage. So this is kind of like your cache problem or your multi-tier memory problem, and it just gets bigger, right? So, in a single machine, you've got your tiers of cache in your CPU, you've got your local memory. When you go to a distributed system, you have all of that, but then you have these more layers, right? You have local disk that might be really fast, like NVMe 2. You might have local disk that's a little slower, like spinning disk. You might have disk over a network. And trying to figure out where stuff should go so that the overall process is as fast as possible is really tricky. And at the same time, we're always trying to maximize cost versus performance. So again, like a lot of times, if you just have a server that you're working on, as long as it gets done when you need it done, you don't really care how efficiently you're using those resources. But once you go up to 10 or 100 or 500 nodes you're paying for in a cloud, your boss at least wants to make sure that this is running as efficiently as possible. So you don't want resources you're not using, but if you don't have any extra space, any extra resource, it's a bit like overclocking. You're kind of at the very edge of kind of crashing things. So it's what makes this generally challenging. At the same time, we have to think about what kind of algorithms we're using, right? Some algorithms just fundamentally cannot scale linearly. So if we throw more resources, we don't necessarily get a payback for those additional resources. What we want is linear or sublinear scaling versus cost. So just to give an example, if you're wondering, in the LLM RAG world, we do a lot of vector search that's a flavor of k-nearest neighbors. So k-nearest neighbors is an example of an algorithm that in the brute force method, it doesn't scale linearly. So that's why we get indices and various other kinds of tricks for getting approximate nearest neighbors or other kinds of mechanisms to get it fast and also linear scaling, but the brute force one doesn't. So there are situations where we have to keep that in mind. And then one of the challenges is also this weakest link problem. So if you have 10 steps in your processing or 10 things you need to do, if you have one of those that's a bottleneck that doesn't scale well, that's going to slow down the entire pipeline. So kind of the slowest piece limits the performance of the whole system. So you may want to take a look at Amdahl's law, which is kind of a mathematical characterization of how fast something can get based on how much of it can be parallelized. So if you can parallelize 90% of your code, it turns out that other 10% costs you more than just 10%, and it gets worse the more you can't parallelize. So some of the things that we want to think about when we're looking at tools, frameworks, and designing systems. So stateful versus stateless processing. So stateless is always the easiest thing, right? Because there's just, there's no state to worry about preserving and synchronizing. There's no data to move. But it turns out that a lot of times we need state, right? Especially LLM apps, right? We have, for example, say a chat model or an embedding model or other sorts of things that are large and we can't function without them, and they're expensive to load and move. So we want to kind of figure out, how do we handle that? Like, how do we get it to the right place, whether it's GPU or multiple nodes, the right number of times, use it as efficiently as possible. Batching, right? So we know that lots of these models and hardware like GPUs will typically perform better for batches. But depending on your requirements, you may have a requirement like an SLA that says, well, you need to take a single request and return a single response in a certain number of milliseconds. And the person that's using your service doesn't really care about your batching, right? So you want batching, but they don't. So you may want to think about how to bridge that gap. Lazy evaluation. So this is another common pattern you may have seen before. Decide what you're going to do before you start doing it. So it turns out that if we kind of plan what we're going to do and then do it, we can do it a little better, which you're probably familiar with from the database world. We want to kind of build that into our data pipelines. And then streaming computation. So we don't want a situation where our system is limited by the amount of memory, whether it's GPU or RAM, in kind of the smallest place. We want to be able to have arbitrarily large data, which means that under the hood, there has to be some kind of streaming mechanism. So even if we don't think about this as a streaming app, if we're doing something to a huge pool of data, underneath the hood, it needs to kind of be able to stream and operate in batches across our hardware. So those are some of the kind of general principles that make this stuff tricky and that influence design of these kind of systems. So let's talk for a couple minutes about Ray and how Ray helps with this. So if you haven't heard of it, Ray is a fully open source project. It's under the Linux Foundation. It was created, I think about 6 years ago, maybe even 7 years ago now, at the beginning at the RISE lab at Berkeley, and it's been evolving very rapidly since then. And the idea with Ray is to have a general purpose, high-performance distributed compute framework that includes management of state. So general purpose, meaning it's not kind of hard-coded to operate on certain particular processing patterns. There are other tools out there that scale very well, but they're hard-coded to work on, say, a MapReduce type pattern or some other kind of pattern. So Ray can handle arbitrary task graphs. That's kind of one of the requirements. Of course, high performance. The whole point is to be the fastest possible, not to do it, but slowly. And then handling state. So from the very beginning, the idea was not just to schedule functions or stateless operations in some cluster, but be able to handle things like reinforcement learning, like model serving, where you have some large expensive state and you need to use it, maybe even mutate it in multiple places in the cluster. So that makes things even more challenging. Within Ray, there's a low-level infrastructure, which has things like the task scheduler, the object store, which, like it sounds, kind of handles managing pieces of state that are the result of computations or that you might need for computations, and fault tolerance, because at scale, you're going to lose stuff. You're going to lose processes. You're going to lose hardware. You have to have that built into the design. Luckily, as programmers, we don't really need to worry about that low-level stuff so much. We get that for free with Ray, and we get a set of higher-level libraries and primitives that we can use above that. So for things like LLM apps, we're going to focus on Ray data, which is an abstraction for moving data around and processing it. Ray train, which, like it sounds, is a abstraction for coordinating training at scale, distributed training. Ray serve, which also, like it sounds, is great for serving models and other kinds of business logic, and a few other tools. One of the cool things about the Ray design is that it's not meant to be like a walled garden where you learn a bunch of special Ray APIs and then you rewrite everything for Ray. That's not the idea. The idea is that Ray is kind of actually a minimal layer focusing on the distributed part and allows you to work with things like LlamaIndex, Hugging Face, PyTorch, all the other tools that you're used to using. So we're going to see later in this presentation, when Simon is showing some of the LlamaIndex code, we can plug LlamaIndex operations a lot of times directly into Ray and get the benefits of both. So we get the beautiful integration framework pieces and simplicity of LlamaIndex, and then the scaling of Ray. So that will be kind of the ultimate goal by the end of this series of webinars. So I wanted to talk a tiny bit about code, just to give a couple of examples, because so far it's been very abstract. And we're going to get into more real code in Simon's segment in just a few minutes. But I wanted to talk a tiny bit about what it kind of looks like to work with Ray to do these things, and give you a little bit of a feeling for the flavor of how this all connects. So this is an example where we might use Ray data to do pre-processing of data of documents at scale for some kind of RAG application. So what we're going to illustrate here is taking a Ray data set, which is an abstraction for some large collection of data that we may want to do stuff with. And we're going to do two operations on it that are both going to be kind of scalable. So one is we're going to generate embeddings. And in this example, we're using instructor embeddings kind of directly from the instructor library, but you could be doing this with LlamaIndex, basically the same kind of pattern. And then we're going to add metadata. And in this example, it's kind of a very trivial metadata. It's just the document length, but we want to kind of illustrate what this looks like. So down at the bottom, you can see I have this paras DS, which is short for a data set of paragraph documents. And we're not going to focus on where that comes from for this example, but we're going to look at two things we're going to do with it. So we've got a document embedder, and then we've got an add metadata step. And what we're doing is calling this map batches operation, which takes batches of data from the Ray data set and runs it through these operations. So the first one is this doc embedder. So like it sounds, it's about embedding documents. And the way we invoke it down at the bottom is we give the class name for the class that describes the embedding. And then we have a compute parameter that tells Ray kind of what kind of scale we want to operate at. And this is telling Ray that we want to use actors, which means we want stateful instances. And the stateful is important because each of these instances will hold a copy of the instructor model. And we want to reuse those instances as much as possible, right? So we don't want to instantiate this model for every batch, right? That would be really silly. But we also just don't want one model and force everything through it. We want to be able to scale, have multiple instances of the model, and use those. So there's a bunch of scaling we can do with that. In this example, I just put 4 of them just as an example. So this will tell Ray that we want 4 class instances that look like doc embedder up there somewhere in the cluster. And Ray will take care of placing those in the appropriate place. We also said num GPUs equals 0.25. So that's kind of interesting because it makes sure that Ray will guarantee that wherever this runs, there is GPU, but it tells Ray that we don't actually need the whole GPU. For these particular actors, if we have a quarter of the GPU, that's good enough. There's other things we can use if we wanted to, say, coordinate whether these get packed onto a single GPU or spread around. So I'm not going to get into all of that, but we could use those sort of things to make sure that these can coexist along with other models. Like we may be featurizing images too for, say, multimodal applications. So maybe this is not the only thing we're running at the same time. And so it's important to have multiple things and have the budgeting correct for placing those on the GPU. So Ray will take care of running this piece. And then we're going to get from map batches another Ray data set, which is this virtual representation of the data. So this will happen kind of lazily. We're not going to have this whole thing materialized in memory. And when we get data from that first operation, we then want to feed it into this add metadata operation. And add metadata here is an example of a stateless operation. So this is even simpler to scale because there is no state. So this will still scale even though there's no new numbers associated with it here. We don't have to supply those because it's so simple. Ray can kind of figure this out on its own. And what we're saying is for every batch in this data stream, run it through this operation. So pretty straightforward kind of idea there. And we have 2 different pieces here, like the doc embedder and the add metadata, not just to demo these 2 different kinds of mappings, but also because it's really nice when we're designing our application, and you're probably familiar with this if you've been building things with, for example, LlamaIndex. It's nice to be able to specify a sequence of operations that are kind of modular so that you can move these things around, compose them to build different pipelines. You don't have to have one giant operation. In fact, you probably don't want to. You want to have separate ones. And then that allows Ray to make the best use of your resources. So maybe the add metadata operation, which doesn't require a GPU, can happen on a CPU or a CPU-only node even at the same time that some other batch is in GPU doing something else. So this is kind of a way that we can make it simpler for Ray to optimize our whole pipeline. The other example I wanted to show really quickly is kind of the last example for my presentation here today is on the serving side, right? So we know that training, we need to train at scale. We haven't talked about that today. We talked about pre-processing a little bit in the previous example. And then we may want to serve this, and this may be serving to the end user, or it may be serving to some other components of a more complicated application. So Ray has a library called Ray Serve, which is designed to make it really simple to do this kind of serving at scale and take advantage of all of the other high-performance infrastructure that we get with Ray. So just to highlight kind of a couple pieces in this code example, which demonstrates serving a chat model using VLLM. To turn a regular Python class into a Ray Serve deployment, which is kind of what Ray Serve calls the fundamental unit of kind of serving logic, we can decorate it with this @serve.deployment decorator, and we can tell Ray things like, hey, this is going to be an actor, so it's going to be, it's going to be stateful, it's going to exist somewhere in the cluster over time. It's going to need 0.9 GPUs, so we can specify resources, and again, Ray will do all the accounting and make sure that this ends up in a compatible place, and we can specify various parameters for auto scaling. So here I just have a simple config that says, well, make sure we always have at least one replica, which is an instance of this class doing some serving, and at most 10. And then there's some other things that we can do if we want to manage how that works. But this will get us a pretty nice scaling configuration just right out of the box. In terms of the code, it's pretty straightforward to use. We've got a class that represents our actor or our stateful object that's going to do the serving. Where we want to manage the expensive state is in the constructor here. So this would be where we load our model, whether it's from disk or from Hugging Face or from a model store or wherever wherever you're keeping your models. We can do some configuration there. And this can be dynamic. In other words, we can use the same template of code here for multiple models. So if you look at that model parameter, that model parameter is configured outside of the class itself. So we could potentially have multiple flavors of accelerated chat here that are actually serving different models just by changing that parameter down at the bind piece at the very bottom. So down there. And then in the get response, that's where we're actually doing the logic. So that's your basic, sampling from the model piece. So the structure is pretty simple, and we can attach this to a more complicated Ray Serve service, which is basically an application with lots of moving parts through this bind. And these services can talk to each other, and we can build more complex systems out of that. So that's just a really quick, very, very quick look at kind of the scaling principles behind Ray and some examples of how we can use Ray for particular pieces of our RAG application. To be honest, although Ray is a really beautiful system and things are working great today, right? We know it's early days in the industry for LLM apps. There's a lot of things that we're still trying to figure out and still trying to come up with the best architectures and the best ways of guaranteeing performance. So just to give an example of places where things are still evolving. If we want to read from a vector store and we want to do that at really high scale, that's not too hard, especially because for example, per some recent Microsoft research, even a single server can end up sufficient for storing a vector store with a huge number of document vectors. So, and we can replicate that as long as we're reading, it's not too complicated. On the other hand, your app might need to do writing and reindexing of a single vector store a lot, whether it's adding documents per user or over time or in some other way. And that is analogous to existing scalable write challenges when we're writing into a database, right? These are kind of hard problems. They usually involve some trade-offs that balance performance, visibility of new data, your application requirements. And so that's an area I think where the industry patterns are still kind of emerging. What are going to be some of the standard patterns that make the most sense for keeping this simple when we're building these applications? So currently it's a little bit, requires a little bit of architecture. Hopefully this will get a little more standardized over the next months. And just to wrap up, if you're thinking about working with your LlamaIndex app and then scaling it with Ray, definitely contact me. I've got my email at the bottom of the slide here. So adamb@anyscale.com. Happy to chat with you anytime about any part of your application, especially the scaling with Ray part. And I want to thank you for kind of taking a look at the Ray and scaling aspects of LLM apps. I'm going to turn this over to Simon here to take you even more into more detail with actual code that runs here in just a moment.
Okay, thanks so much, Adam. That was super informative. I think I learned a ton from listening to your talk as well. Yeah, I hope everyone learned a little bit about the general aspect of scaling up these large language model applications. So as a next step, we're going to work a little bit more hands-on with a specific Jupyter notebook where we leverage LlamaIndex and Ray to build a specific application. So I'm going to share my screen now and get started on the next part. Okay, hopefully everyone can see my screen. So I'm going to very quickly talk about setup, but largely skip it over. So for the sake of time, please follow along as I go through the notebook. And if you want to kind of recreate the experience, all of these are available through a public GitHub repo. So all you need to do is git clone the repo. There's a couple of setup steps. First of all, you need to create a Python environment and install the dependencies. And there's the extra step where you want to set up a Postgres DB locally in this case. We provided a very simple Docker Compose script in which you can just run Docker Compose up, and you should have the Postgres DB running in the background. As the next step, you go to your terminal, run Jupyter Lab, and then you should be able to find the notebooks that we'll go over today. So what are we building today? So we're going to use the Ray Docs Assistant as an example large language model and specifically retrieval augmented generation application. So the Ray Docs, as you can imagine, is a set of HTML documents that's hosted to give you information about how to work with Ray. And the goal is to create a conversational assistant agent in which you can ask questions and get really high quality answers and build that in a very scalable way, both from the indexing side as well as the application serving side. So we'll go into a little bit more detail about what that actually means. So if you're at this workshop, you probably already know what a large language model is and its limitation in terms of how it's only trained on public data. So since previously it had a knowledge cutoff of 2021, there's no way for it to understand anything about the Ray documentation since a lot of it is created after that knowledge cutoff date, right? So this is where retrieval augmented generation comes into play, where you really want to build a knowledge base over your custom data and to be able to retrieve information from that knowledge corpus and then give it to the large language model to reason at the query time. So how that works is at a high level, you have a query, you need to pass it through some embedding model. So that converts the text into the list of floating numbers that represents its semantic meaning and use that to retrieve a set of relevant context information and then pass both the query as well as the retrieved context to the large language model to be able to generate a response. So hopefully everyone's on the same page in terms of at a high level what architecture looks like. So let's dive right into the notebook for the sake of time. Okay, there we go. As I've mentioned, you have access to this notebook just by git cloning the repo and then running Jupyter Lab, and you'll see exactly the same view. I'm going to make this a little bit bigger. Okay, hopefully everyone can see my screen well. For the folks who weren't here a little bit earlier, this will be a 3-part workshop. So in this first part, we're going to be developing the Ray Docs Assistant application, leveraging LlamaIndex and the Ray distributed computing engine. So in this notebook, we're going to learn to develop this application and specifically scale the embedding and indexing part of the application. In terms of setup, so I already have my OpenAI key set up in my environment variable. So I'm just going to skip through this. A lot of the computation being done in this particular notebook will be relying on the OpenAI large language model as well as the embedding model. So as a first step, you need to do that setup. Now, the first step of building a retrieval augmented generation system is to first load, parse, and embed the data that we want to use for answering our questions. There are at a high level, like 3 steps. First, we need to load the latest documentation from Ray. So these are sort of HTML documents. Then we need to parse the documentation to extract out relevant chunks of text. And here specifically, we need to make sure the chunks of text are of reasonable size so that it fits into the context window of both the embedding model that we'll be using, as well as the large language model that will be reasoning over that. So given that chunking operation, we, as the next step, need to embed those chunks. So what that's doing is passing through the text chunks through an embedding model to create a vector representation. And this vector representation allows us to determine the similarity between 2 different pieces of text snippets and allow us to retrieve the relevant contextual information given a question that a user might have. After that, after those representations have been created, we need to put that into a vector database. And in this case, we'll be using Postgres for convenience. It will be an external storage in which both the textual representation and the embedding will be stored to allow very easy retrieval at query time. Okay, so within this whole system, you can see that like a lot of these operations have the corresponding abstractions defined in LlamaIndex, which help you build these very easily without going through the exercise of rewriting some of these code. And we'll be leveraging Ray as sort of as a orchestration layer or distributed computing layer that stitch together a lot of these operations so that they're being run in the most efficient way across different machines that you might have in your cluster. So in this particular case, we'll be working on my local laptop, so there will be really a single node. So it's sort of a quick demo, but everything should work the same when you have a node of, let's say, like 5 or 10 machines which you can parallel this computation over. And specifically within the Ray ecosystem, we're going to be using the Ray data library, which is a higher level abstraction over the low-level remote execution engine. And that is used to scale out the data processing pipeline and will allow us to process a lot of these data in parallel and much faster. Okay, so diving into the code itself. So if you are cloning the repo, we'll already have the Ray documentation HTMLs downloaded into the repo itself under like under the parent directory of datasets. So the first step is unzipping all the documents into the HTMLs. As the next step, we're going to load all the HTML files given the path that we've specified into the Ray data pipeline. So as you can see, we've loaded around 3,000 documents here. So each document right now is a full HTML file. So now we're going to be leveraging a component called HTML tag reader provided by LlamaIndex to extract out relevant sections in our HTML page and to be able to create, starting to create some data representation that will be used with LlamaIndex. So in this case, a document object. So very quickly, so this is an illustration of what is happening under the hood. So within each HTML file, the Ray documentation is defined in different sections. So for example, in this particular page, talking about the environment capabilities in RLib, there are 2 high-level sections, the environment and configuring environments. Leveraging the HTML tag reader, we're able to extract these out as separate document objects in LlamaIndex and add relevant metadata so that we can very easily retrieve the relevant information at the query time. So specifically, we're parsing out the text from the HTML tags, as well as like adding the specific the anchor section anchor information into the source metadata. So concretely, going through the code itself, we're going to import a HTML tag reader from LlamaIndex.readers. So within LlamaIndex, there's more than 150 different type of data loaders and readers that allow you to very easily connect to different APIs and to be able to parse different kind of documents. So you don't have to worry about all the dirty work yourself. So here we're going to write some very quick helper functions to be able to map from the path of our HTML page to the URI that we want to use for identifying what the documentation is about, as well as the helper function on just extracting the section and setting up the data in the right format. So given the documents that we've loaded from our data set, we're going to run the extract section helper function on a single document. So you can see that, and this is the output where we've extracted out the relevant text and also appended into the metadata the relevant document sources. So this is just operating over one example. And now we can use Ray data to very easily parallelize this across all the HTML files. And by leveraging Ray data, the whole aspect of which machine to run which subset of computation over the data is completely transparent, so we don't have to worry about that. All you need to do is basically call this flat map function that Adam has talked about earlier. So this will be applying the extract section function on each of the HTML files, and then gathering multiple document objects from each HTML files and creating a flat list over that. So now first step of mapping, and then second step of like kind of gathering all the resulting document objects and put into a flat list. So as you can see here that the output, it appears immediately. So this is because Ray data is lazy by default. So what's happening is that like as we're creating these operations, it's getting defined but not executed immediately. So at the end of the pipeline, you'll see that when we trigger the final operation, the full computation starts executing across these different operators. And this allows Ray data to fully optimize the resources across these pipelines, across different index operations. Okay, now that we have a list of document objects, which contains the text and source for each sections, we need to do another step of chunking the data. And this is because the document object that we have right now might have sections that are very, very long, including thousands or tens of thousands of tokens. And what we really want to do is make sure that we have manageable chunks so that they could be indexed independently and processed by the embedding model and the large language model within the context window limitation that they have. So typically, so for the large language model, there's a range of like thousands of tokens for the context window. For text embedding 02 offered by OpenAI in terms of the embedding model, it has a maximum length of around 8,000. So in this case, and but some of the open source models for embedding have a much smaller context window limitation, approximately 512 to 1,000. So in this case, we're going to pick a reasonable chunk size that could be accepted by a wide range of models. So here we're going to do 512. And this chart just shows a distribution over section length in the document object that we have processed above. You can see that there's quite a bit of outliers for some of them. Okay, so in order to do the chunking operation, we'll be using the simple no parser abstraction in LlamaIndex. So this specific component basically does sort of the most straightforward sentence-based splitting. So under the hood, it's going to automatically choose the right breaking point so that it preserves full sentences within the textual documentation, while still making sure that the full text chunk size falls under the limitation that we've specified. So here we'll pick a chunk size of 512, use the simple node parser to run the chunking step. So here, let's go through one single example first. So you can see that we are taking the data set specified before with our section documents. We're going to take a single one and then run this computation over it. So you can see that this document, since it's already within the limitation, will be just getting one single chunk. But for some of them, you'll see that like it'll be generating 5 to 10 chunks. Okay, now we'll be applying that operation as another operator in the Ray dataset pipeline. And here using flat map again and running the chunk documents. So similar to before, this should return almost immediately where, yeah, the operation is being queued up so that it can be run later. Okay, now that we have parsed the documents into parsed the HTML into document objects, and then split them into manageable chunks, we need to embed the data. So here, there's many options that you can use across Hugging Face, open source embedding models, or various model providers implementations as well from OpenAI or Cohere, for example. The goal here is to basically leverage these models to create semantic representation of the data so that they can be easily retrieved to give the most relevant context information. So here we're creating a helper function that is able to use either the text embedding Ada-over-2 from OpenAI or a local Hugging Face embedding model. So to note that like in order to run some of the open source models, this will be downloading the model weights onto your local machine. And so in the context of a Ray cluster, it will be downloading that to each of the worker nodes in the Ray cluster. And one of the consideration is to be able to kind of manage, like cache that state of the model information and use that across multiple runs. So as Adam was mentioning here, we'll leverage the ability for Ray data to accept a Python class to encapsulate the embedding logic in which it will be caching the embedding model that you're using and then applying that on each of the calls to process the data without re-instantiating the model every single time. So in the case where we're using OpenAI, this is not as important because the OpenAI model, the embedding model is behind an API, so it'll be sending that request to a remote server and not needing to download the model locally. Okay, so after we have the helper function set up and embedding chunks module set up, in this particular case, we're going to use the OpenAI embedding model just because I'm running on the laptop and running the local embedding model, at least the larger ones, it'll be a little bit slow. But in the case of a Ray cluster, generally we will recommend using, for example, one of the best rated open source models out there. In fact, we've seen a lot of them perform on par or even better than OpenAI or the vendor specific models. The main difference is that like a lot of them have limitations, like a smaller context window limitations. So for example, the GT base, I believe is, I think 512 token limit. Okay, so now that we have our transformation module defined, we can try it out on an example chunk. So similar to before, we can take one batch of chunks out of our data set and then apply our embed chunks operation on top of that. Okay, so to see what this looks like, now we have both the text representation of the document as well as a list of floating numbers representing the embedding for that. So you can see that, yeah, we have completed that embedding with the embedding size of 1500 for OpenAI Ada-2. Okay, now that we have those operations, we can run that on the whole data set again. So here, running map batches so that we're grouping batches of these chunks and then applying the embed chunks operation on each batch. All right, so we're getting close to sort of the end of the notebook. So we have our embedded chunks. The last step is on the indexing pipeline is to be able to store them somewhere so that we can retrieve them easily for inference. So there's a ton of different vector database options. For this case, we're going to use Postgres for its simplicity. So we've already spun up a Postgres database locally. And in the slides I showed earlier, we have the instruction for how to use Docker Compose to spin it up. So in this case, we will create a table called table containing all the information that we have to build our application. So this will be the raw text information, the metadata information containing the source of where that documentation page is coming from. And then lastly, the embedding that we've generated into a single table so that we can at query type retrieve the relevant text information by matching against the embedding of the query to the embedding of the text. Okay, so the code afterwards assumes that you have the PostgreSDB has launched. And just to be safe for the first step, we're going to drop the table that might already exist there. So within LlamaIndex, you can configure the table name to be used to store these different collections or indexes over documents. And here we're using data documents as the default. And first step, we're creating a function to be able to connect to our Postgres store. And this is leveraging the integration exists in LlamaIndex to simplify a lot of the underlying operations. Trust me, you don't want to write the connector code to the pgvector yourself. So we'll prefer you to just leverage what we have built. Just setting up some straightforward connection informations, and then specifying the table name that we want to store this index in. One thing to note that is for the pgvector store, you need to first specify the size of the embedding model that you're going to use so that you can index it efficiently. So here, since we're using the OpenAI embedding, we're going to use 1536. Now, as the next step, similar to the embedding model part that we went through, we need to create a Python class to store the connection to the Postgres store and expose the callable function where we can take in a batch of embedded nodes and actually put that into the vector store. So here, since we're using LlamaIndex vector store integration, this is super straightforward. You can just call the .add operation with the list of embedded nodes that we've obtained before to be able to efficiently add that to the vector store. Now that we have this operator defined, similar to before yet again, we're going to use the map batches operation, operating over a batch size of 128 across multiple workers to be able to ingest data into the vector database efficiently. And since this is that last step in the pipeline, we're going to call count, which is going to trigger the entire pipeline to run. Okay, so here we're waiting for the pool of actors to get started. And then you can see now we're happily chugging along over, I guess, the entirety of the resources available on my tiny Mac to do the processing and ingestion into the vector database. Okay, so this might take a little bit of time just because everything is running locally. This should be much snappier on a real Ray cluster. So we'll let it keep going. So afterwards, if you were to check your Postgres table, you should be able to see that we have around like close to 10,000 different document chunks that's being ingested and indexed into that vector store. Okay, so at the end of this section, it wraps up all the processing that we need to do in order to index the documents. And now we just need to define the application logic to do the retrieval and generation aspect. So in the second step, we want to essentially pull the relevant context given a query. And so here we'll be using the same embedding model to embed a user query that may have, and then use that query embedding to match against the embeddings of the text documents in the vector database in order to retrieve the most relevant information. So here we're going to use a couple of abstractions from LlamaIndex to do this. So first of all, we're going to use the same function to connect to the Postgres vector store as before. We're grabbing the same embedding model that we defined before. So in this case, it's the OpenAI. Now we need to basically define a service context in LlamaIndex. So here is very much specifying which embedding model or LLM that the overall framework should be using. And we'll be using a vector store index class and pass in the vector store that we already have and the service context so that we have access to the index abstraction. And as the next step, we can build a retriever on top of the index and specifically configuring it with the number of relevant chunks here. So in this case, we're going to retrieve the top 5 chunks. So let's try to run this very quickly. Over the question, what is the default batch size for map batches? So very relevant since we're just using this function. So the retriever is going to be able to retrieve a list of 5 nodes as we specified. And if we print out the content, you can see these nodes are retrieved based on the vector similarity, and you can see the score of how well the text chunk matches the query, as well as the specific text that's retrieved. So super straightforward. And then now we have the next step of response generation using the retriever that we have built. So concretely, like what's happening here is basically combining the query information and the top K context that we retrieved and leveraging a specific question answer prompt to be able to generate a final response over the knowledge corpus that we have. So creating this end-to-end query engine is super straightforward with LlamaIndex. And here you can use any large language model of your choice. So in this particular example, we're going to use OpenAI, but Anyscale also offers these endpoints that are super cheap and efficient, and you're able to basically run open source models like Llama 2 and various others through the Anyscale endpoint as well, and it will work almost exactly the same as the OpenAI API. So for the sake of demonstration, we're going to use OpenAI from the LlamaIndex LLM integrations. We're going to use the GPT 3.5 Turbo, which is the cheaper and faster version of the model, setting the temperature to be relatively low so that we have high quality responses that are slightly more deterministic. We're going to find the same embedding model again, and then this time construct the service context with the large language model and the embedding model specified. So this will be very much the same as the previous section. So I'll skip over. The main difference is that instead of calling sRetriever to build a retriever, we're going to use a higher level function called sQueryEngine to directly get a question answer endpoint over the index. So here you can just send the question to the query engine. And then now let's see the response. So yeah, so since both the query and the response are quite small, you can see that the LLM actually returned almost instantaneously with the desired result that we wanted. And yeah, we've double checked many of these. The quality is pretty good. You're able to find pretty reasonable answers over the Ray documentation. And here specifically, you can very quickly learn that the default size for map batches is around 4,000. And here we're also printing out all the source node information so that you can validate these responses as necessary and print out a list and make the response a little bit more interpretable. So here we have the top 5 nodes, which should be exactly the same as what we saw in the previous section when we ran the retrieval. And then, yeah, the large language models, given the prompt, is able to extract out the most relevant correct answer out of these list of reference information. Okay, I think that is approximately the end of this first notebook and the first hands-on tutorial. Yeah, so thanks everyone for listening, and hopefully you learned a thing or two about how to build a retrieval augmented generation system leveraging LlamaIndex and Ray. Just to say a couple more words, feel free to get in touch with us about more questions or anything you want to learn more about in terms of Ray as well as LlamaIndex. So we have this link you can use to sign up for office hours, in which we're happy to provide additional support in helping you build production-ready applications with LlamaIndex. We also have a newsletter in which we send out every week with the latest things happening both in LlamaIndex as well as in the ecosystem broadly as well. So we'll definitely help you keep updated with all the exciting things happening super fast in this ecosystem.
Yeah, and just to add on, like Simon and Adam did a great job presenting the overview of especially in the first course of this workshop. And just to be clear, there are parts like 2 and 3, and we'll have like a follow-up session because a lot of this is, okay, so you set up like LlamaIndex and Ray to build like an initial pipeline. Now, how do you actually, figure out how to evaluate and optimize it? And so all this stuff is going to be super relevant, and it's kind of following the user journey from building the initial stuff to the hard stuff to productionize. So thanks everyone for the time. I think we're around near like rounding out the hour. And Simon, feel free to add a few words if you want, but otherwise, thank you, and we'll see you next time.
Yeah, thank everyone for joining, and see you next time.
Thank you. Bye.